Hi everyone and welcome to this episode of Kuiper Labs. In today's video we're going to be discussing molecular structure. So building on some of the concepts that we've looked at so far in terms of how molecules are connected together, how atoms can be bonded together in order to make a molecule in a molecular compound or even just molecules generally, and what that's then going to be able to tell us about how molecules interact with one another. So I'm going to first of all, we're going to have a look at a molecule of hydrogen gas. Okay, so H2. Okay, so hydrogen as an element exists as what we call a diatomic molecule. Okay, so with two hydrogen atoms connected together. When we've looked at drawing a Lewis structure, we've looked at this idea that we can say, all right, well, this hydrogen over here has one valence electron, and this hydrogen atom over here has one valence electron, that then as they come together, as they connect together, that these valence electrons become shared between them to make a bond that joins those atoms together in a way that's hard to undo. And we call that a covalent bond. Okay, so we're talking about a shared electron pair. Okay, and this connection is what requires a significant amount of energy to break, and so we've been able to now identify that involves each atom contributing one valence electron to make that connection, that shared pair. That shared pair helps to provide each atom with a full valence shell, and so then that makes it more stable as the molecule comes together. But the reality is that this Lewis model of bonding, that was kind of this shared valence electron pairs to connect atoms together, is also not quite accurate enough, and it relies on a change that occurred in the atomic model since Lewis proposed his idea in 1916. And what it was is that Lewis had been looking at this idea of Bohr's model of the atom, and so seeing that electrons orbit in defined energy shells, which are like planets going around the sun, that each one has a different amount of energy, and the electrons maintain, stay within that orbit, but that those orbits are otherwise well defined and very regular. Just like, we can predict the position of any of the planets on any given night, from now until forever. Because we've been able to study how they move. But the reality is that since Bohr had proposed this model, we recognized that at the atomic level, that the behavior of things is not quite as consistent as it is with big objects like planets in a solar system. That electrons that orbit are actually much more chaotic, much more random, and unpredictable in their behavior. So, one of the fundamental ideas is called the Heisenberg uncertainty principle, that you can't pin down the position and the momentum of an electron at together at any given time, that you can only know one when not the other. That because electrons are much more random, the model of the atom has been updated to make what we call the cloud model, where if this little blue dot represents the proton in a hydrogen nucleus, that rather than being a nice kind of well-defined sort of orbit, that we have this cloud or kind of boundary in which, now this looks like a preschooler's drawing, I totally get that, that the electron of that hydrogen atom could be found somewhere within that boundary, somewhere within that cloud, but at any given moment we have no idea where. It's more defining it as an area of probability rather than a specific place and time. And so this is kind of the model that we need to be kind of taking forward from here, as far as saying, okay, well, valence electrons still exist, that these electrons that are shared between these hydrogen atoms still exist, they still form this connection which is hard to undo, but that rather we can actually kind of picture, rather than these kind of particular electrons that are kind of being reached out from one atom to another in this really well-defined sort of thing, that actually it's kind of more like that the clouds overlap to share these electrons. And so we have the cloud of one hydrogen atom, and we have the cloud of another hydrogen atom, and when they were separate, look like this, and then as we bring them closer together, that then these clouds get to a point. This diagram looks terrible. It also rather descriptive in its own way, that these clouds overlap and when we're forming a molecule. So we still have the nuclei, we still have the protons in each nucleus, that there's a gap still between them as far as that the nuclei can't get too close to each other, but there is a certain overlapping of their clouds which allows them to become more stable in energy terms. And so this is our cloud model of hydrogen gas. Okay, so I appreciate that it looks like a whole bunch of scribble, but that's quite relevant in that respect. And so what that then means, aside from me having just used up a whole lot of ink to show you that, is that now if we want to picture a molecule of hydrogen, now I'm not going to scribble to kind of show you the cloud, I'll just kind of show you the outside of the cloud, is that instead of this cloud here and this cloud here, and then kind of them just kind of, as we come close together, that they kind of overlap, is that when we form the molecule, is that we actually, just like, say, two people in a relationship forming, forming a marriage or something like that, where they become a single entity, that then that hydrogen molecule now has a combined electron cloud. Okay, that they've overlapped to the point at which that they've melded together into this one thing, that there's no defined boundary between them anymore. And so that the electrons that are in that molecule are actually able to move all the way throughout that molecule. That the electron from this hydrogen could be found over up this end and vice versa, that they're not fixed around their original atom anymore, that this sharing arrangement means that they've kind of blended into this one mega cloud. And so what that then means, or impacts in terms of how molecules interact with each other, is that, so we've got, if I just kind of draw, we've got two electrons in this molecule, okay, because it's the simplest molecule that we can come up with that's got two atoms. That maybe at some point, as these electrons are randomly, chaotically whizzing around, that both of these electrons end up this end of the molecule, and that means that there are none down this end. What that means is that if we look at the molecule as a whole, that this end of the molecule has a slight positive charge, and this end has a slight negative charge. Now, so we could say plus and we could say a minus to show the arrangement there, but the reality is that because this is such a brief kind of moment in time where these electrons might happen to be down that end at some point, that it's not really the same as like a full positive and a full negative charge. It's actually just the tiniest fraction of charge imbalance. Okay, and I'll write that phrase down here just to kind of prompt you. So charge imbalance. And so what we do is we say, it's all right, well, there's a slight change in charge, a slight positive and a slight negative. And so we actually then add a little lowercase delta symbol in Greek, which, so, capital D delta looks like this, lowercase d delta looks like that. So it's kind of like a backwards kind of 8 sort of, or a 7 with a circle at the bottom, or I don't know. That's not super crucial. As you can see, my drawing's not perfect either. But the idea is that we have a slight positive charge and a slight negative charge at the opposite ends of this molecule for that moment. Now, the reality is that, perhaps a nanosecond later that the electrons have evened out, or maybe they're both up this end or whatever. But that for that tiny snapshot in time that we had a slight difference in charge from one end to the other, we had formed what's called a dipole. And so it's a very, very temporary dipole. So something that's a dipole has one end being different to the other end. Oh, they're opposites, positive end and negative end, and it's really, really temporary. But what that means is that then, let's say that this molecule at that moment in time has this sort of position, and we have another hydrogen molecule that's over here with its little combined cloud, okay, because they happen to be near each other. And let's say this molecule happens to be doing the same thing. And so it's got a slight positive and a slight negative as well in the same sort of arrangement. And so what that means, if I pick a different colored marker, because production values, that then all of a sudden in that brief moment of time that we have a little force of attraction. So force of attraction between the negative end of this one and the positive end of that one. And so what that means is that then, just for that brief kind of moment in time, that there is a little bit of a pulling force that keeps these molecules together. A fraction of a second later, it's gone. But what that does is that when we have more and more and more molecules near each other, that these forces of attraction are constantly blipping in and out between molecules all over the place. And so that what that does is that then that force of attraction is actually pulling these molecules together and holding them together in a way that, because of the sense of scale, because of how many molecules we're talking, becomes very large. Okay, so we've talked about this idea that atoms, that we're updating our model of the atom to the cloud model of these areas where electrons can be found, that when we form a molecule that these clouds overlap and become one big cloud. And what that means is that then that cloud of electrons is able to shift and move to create what we call temporary dipoles. And those temporary dipoles can interact with each other. And so what we're going to do is we're going to look at that kind of basis, and we're going to build on that to look at a range of different intermolecular attractions or forces that can exist. All right, thanks very much for watching. Bye for now.